Welcome back. In this segment, we're going to illustrate the algorithm to solve LHRRCCs using a concrete example. In fact, we're going to solve this recurrence relation which we saw in a previous segment. Before we apply the algorithm, we must always check that the recurrence relation is indeed a LHRRCC. That's the case here. I'll let you check it that the recurrence relation is linear, homogeneous, and has constant coefficients. Since this is the case, we can perform the first step in the algorithm, which is to transform this equality by first moving all of these terms to the left-hand side, and then use this equation to build the characteristic equation of the recurrence relation. And the way we do that is we replace a sub n by a variable, let's say r, to the power what? Remember, we need to replace n by the order of the recurrence relation. Here the order is 2, so we can have r squared minus 3 times r to the power 1, because 2 minus 1 is 1, plus 2 times r to the power 0, which is 1, because n minus 2 is 0. So here is the characteristic equation of this recurrence relation. So the next step, of course, is to solve this characteristic equation. By the way, this is a quadratic equation because the polynomial on the left-hand side is a polynomial of degree 2. So I strongly encourage you to go back and review your quadratic equations and the algorithm to solve them. Here, there is an easy way to solve it if you notice that 1 is a solution or a root for this equation, because 1 minus 3 times 1 is minus 2 plus 2 is 0. So you might notice that the first root r1 is 1, and therefore the second root must be 2, because the first root times the second must be equal to the constant term 2. So 1 times 2 is 2, therefore the second root is 2. Now if you want a systematic way of solving these equations, these quadratic equations, then please make sure you go and review that algorithm. Finally, the third step in the algorithm is to use these two roots, after you check that they are indeed distinct, to write down the general form of the solutions to this recurrence relation. Now remember, the formula goes like this: a sub n is equal to alpha 1 times 1 to the power n, which is just 1, and plus alpha 2 times 2 to the power n. This is the general form of the solution that the algorithm gives us. Now remember that every recurrence relation by itself has an infinite number of solutions. Basically, there's one solution for each pair of values for alpha 1 and alpha 2. Now remember that we already discussed this recurrence relation, and in particular we discussed several solutions in a previous segment. Remember that one of the solutions had the form a sub n equals 5. So how can we produce that particular solution using this general form? In other words, what values of alpha 1 and alpha 2 should you pick for a sub n to be equal to 5? Well, you can take alpha 1 to be 5 and alpha 2 to be 0 in order for this power of 2 to disappear. So this is a particular solution sequence to this recurrence relation because you pick two particular values for alpha 1 and alpha 2. Now remember that we found another solution to this recurrence relation earlier, namely this one, 2 to the power n. So why don't you go ahead and find the specific values of alpha 1 and alpha 2 that produce this unique solution starting from this general form. You got it? Alpha 1 must disappear, so you put a 0, and alpha 2 must be equal to 1. And let me ask you the same question for the third previously discussed solution, namely 3 plus 2 to the power n. Again, this is pretty easy. You just want to have a 3 here for alpha 1, and you just want to have a 1 again for alpha 2 to get this particular solution out of this general template. So while there are an infinite number of solutions to any recurrence relation, there's only one solution once you match it with a set of initial conditions. So the next exercise will be for you to start with this recurrence relation here for A sub n, and then I'm going to add a pair of initial conditions. I need two initial conditions because in the recurrence relation here, n must be greater than or equal to 2. So I'm going to need to fix some specific values for A sub 0 and A sub 1. So let's say A sub 0 is 3 and A sub 1 is 5. By the way, this is called a recursive definition, remember, because it's composed of both a recurrence relation and a matching set of initial conditions. So we know there's only one solution to this recursive definition, and I want you to find it. I want you to find a closed form formula for A sub n. How are you going to do that? You're going to use the general form of this recurrence relation, which is part of this recursive definition. And then I want you to use these two specific initial conditions to determine the particular values of alpha 1 and alpha 2. So come back when you're done and to check your answer against mine. So the way to solve these kind of problems is to start with the general formulation of the solution, which we obtain here, and then to use these initial conditions to determine the values of alpha 1 and alpha 2. So first use the first initial condition for n equals 0. What do we have? Well, we have A sub 0 is equal to alpha 1 plus alpha 2 times 2 power 0. Of course, 2 power 0 is 1, so an A sub 0 is 3, so we have 3 equals alpha 1 plus alpha 2. And then you repeat this process for the second initial condition when n is equal to 1. So you have n equals to 1, which means A sub 1 is equal to alpha 1 plus alpha 2 times 2. 2 power 1 is just 2. So A sub 1 is 5, so we have 5 equals alpha 1 plus 2 alpha 2. Now we have two equations with two unknowns. Now remember we're trying to solve for alpha 1 and alpha 2. That should be pretty easy. In this case, you just subtract this first equation from this one. So 2 times alpha 2 minus alpha 2 will give you alpha 2. Alpha 1 minus alpha 1 will cancel out. And 5 minus 3 will give you 2. So alpha 2 is equal to 2. And then you can use the first equation to infer that alpha 1 must be equal to 1. There we go. We have the general form of the solution. Here we have the specific values of alpha 1 and alpha 2 that satisfy these initial conditions. Therefore, the final unique solution to this recurrence relation plus initial conditions is just the generic form here after you plug in the values of alpha 1 and alpha 2. So I'll let you check that if you plug in a 0 for n, you get 3 back. If you plug in a 1 for n, you get 5 back. And then you can just compute the next few values for fun.